All right. So last session we talked about the properties of concrete, Portland cement concrete, and the basics of concrete mix design. But today we're going to talk about the steps to design a concrete mix or concrete proportioning mix. And we see what requirements we need to design the proportions in the mix of Portland cement concrete. So the first step is strengths requirement. Step 1, strengths requirement. And this is probably the most important one because one of the main or ultimate goals of designing a concrete is reaching a specific range of strengths when the concrete is hardened. And that's exactly why we are designing the concrete to have a specific range of strengths for different applications, let's say for structural applications, or if it's a pavement or if it's a structural element, we need different strength requirement for these elements. Now, how does this work? The design engineer, which all of us we're going to be, so design engineer, you specify the strength requirements. So when we design a structure, or when we design an element that has concrete material, again, let's say a concrete pavement or a concrete beam or a concrete dam, we design, once we are done with the design, one of the final outputs of the design is what is the strength of that concrete element. And if you are taking concrete design or structural analysis, we call this F prime C. That's the compression or the compressive strength of the concrete, which is the design criteria. Now we need to know that concrete strength is variable. So concrete strength is variable. And we kind of designing the concrete in a way that we assure that the final product is having the minimum requirements. So it means that the final product can have a higher level of strength, but it cannot be lower than what the design engineer has designed and required for the concrete element. So the design strength should be met by the design criteria and mixing process. Right? Okay, so a little bit of mathematical background regarding how the design process, how the strengths parameter works. Now, if you remember from probably statistics, you probably remember the bell curve, right? So if you remember the bell curve or normal distribution, this is, we call this a normal distribution, right? So normal distribution. And it just shows the frequency of your data in a population and how they are arranged around mean. The one or the value which repeats more or the most in the data population is the mean value. So this is mean or average, right? And let's, for our purpose, let's call this F prime C critical. That's the average strength, right? And then again, if you remember from statistics, from this curve, we can have, or we can specify the range of variations, which is in this case standard deviation. Or sometimes they call it S, sometimes they call it sigma, right? And what we want is, if you again remember the confidence levels or confidence intervals, for each confidence level we have a certain limit of allowed standard deviation range, right? So what we want is, we want our F prime C within 1.34 of standard deviation or sigma. Right? So how we can formulate this is that F prime C, or the critical or the average, we call this average strengths for the mixed design, is equal to F prime C, whatever we get from the test, plus 1.34 standard deviation. Right? So F prime critical or average, let's call this the average strength. So this is the average strength for mixed design. And then by adding 90%, by adding 1.34 standard deviation, so adding 1.34 standard deviation to F prime C, we are within 90% of the confidence level. That means that 90% of the concrete will be stronger than specified strengths. Right? So let me fix this one. So again, by being within 1.34 standard deviation of the average, we are making sure that by 90% confidence level, we can say that, or we can say 90% of the concrete samples, if we take different samples, will be stronger than our F prime C, which is the required or the design strengths, right? Okay, so we can say this when this is true when standard deviation is less than 500 psi. Now, what happens if standard deviation is not less than 500 psi? So if standard deviation is greater than 500 psi, we can rewrite the equation as F prime C, the average will be F prime C plus this time 2.33 standard deviation minus 500 psi. And again, if we want to specify this, S is standard deviation of F prime C. Right? Okay, so that's basically the general rule to find out what is the average strength requirement based on the design strength requirement. Now there are other tables when you have very few samples for a small number of samples. So there are adjustments. So adjustments for small number of samples. Small number of samples. For example, if you're specified, so let me, okay, so if your specified compressive strengths, or F prime C in megapascal or in PSI, if your F prime C is less than 21 megapascal or less than 3000 psi, then the required average compressive strength, this is the required average compressive strength, or as we call it, F prime CR or F prime CR, again in terms of megapascal or PSI. So if you have less than 3000 psi, then F prime average, F prime C average is F prime C plus 7 times F prime C plus 1000. If we are between 21 to 35 megapascal, or 3000 to 5000 psi, then we have F prime C plus 8.5 or F prime C plus 1200. That's the first one is megapascal and the second one is PSI. And if we have greater than 35 or greater than 5,000, then we have F prime C plus 10, that's in megapascal, or F prime C plus 1400, that's in PSI, right? So that was step one. So if you remember, if you go back here, that was step one. That's the strength requirement. Okay, let's go to step two then. Now, step two is determining the water to cement ratio. So determining the water to cement ratio, or W2C ratio, right? Now what we do is we use the historical data or the previous lab results, historical records of the strengths are used to plot F prime C versus water to cement ratio. And we had this before, this graph before, but the general rule is the higher water to cement ratio is lower strength, right? So if this is water to cement ratio, and this, the y-axis is your F prime C, or compressive strength, again, the higher water to cement ratio means lower strength. And we have two trends. The first one, the continuous line, is when you don't have any air voids in the mix. So this is non air entrained. And this is when you have air voids in the mix. So this is air entrained. And again, if we want to show the comparison is for, let's say for this amount, you have this much strength. If you have lower water to cement ratio, you have higher strength, right? So that's the general rule. But we need to check for the maximum allowed. We need to, okay, so check for maximum allowed water to cement ratio, right? Why we need to check for that? Because severe exposure requires lower water to cement ratio. So severe exposure conditions requires lower water to cement ratio. And then we, from the graph, we always want higher compressive strength, right? So we need to use the lowest possible water to cement ratio. So we need to use lowest possible water to cement ratio based on exposure conditions and also based on sulfate exposure, specifically for sulfate attack, right? And then there's a table from ACI. We've mentioned ACI before, but ACI is American Concrete Institute, and they have the most important standards, following standards for design of concrete. Course notes that I post later on. This table will show the W2C adjustments. So this will be ACI water to cement adjustment based on exposure. And I'm gonna paste the table here after our meeting. Okay, so that's based on general exposure, and then there's another table again from ACI. So it's another table from ACI that will be again the W2C adjustments for sulfate exposures, again from ACI. From ACI, right? So that would be all you need for the step 2, which is the water to cement ratio requirements. Now, the third step, step 3, is requirements for coarse aggregates. So step 3, coarse aggregate requirements. Okay, so of course, for when we're using aggregates, the first and most important thing to consider is the gradation and what is the maximum size, right? So, of course, gradation and maximum size or the maximum particle size of the aggregate. And the general rule is we want to use larger particle size because that would be economical because you are filling most of the concrete with the aggregates. So use larger maximum particle size. And of course we want dense gradation, right? Because that would give you higher strengths. So denser gradation. And of course, these are for economic reasons, right? More economical. And then there are physical parameters or particle properties. So particle properties in terms of what are the shape. We don't want flaky and elongated aggregates in the mix. What are the texture? We want definitely some roughness. We don't want very smooth aggregates. And what are the porosity? We want to know how much air voids we have inside the aggregate particles, because that affects our mix design and how much water we need to add to the mix. And there are some general rule of thumbs that we need: round and smooth. So round shape and smooth texture. We want these only for having a workable concrete. So for more workability. And again, workability is the ability to work with concrete, and when you're pouring the concrete, then if it's workable enough, it can go around the rebars and fill all the gaps between the rebars. Water and cement. So these are the ideal conditions that we can, the higher aggregate content, we can use less water and less cement, and that would be much more economical because the cost of cement production is much higher than the aggregate. And then there's another table for the maximum aggregate size, that the nominal maximum aggregate size that I'm going to pay. Sorry, I was disconnected for a second. Let me go ahead and share screen again. All right, we're back on now. Okay, so I was talking about the nominal maximum aggregate size for different applications. And then again, it's based on what type of dimensions you're looking at. You have different applications, and it's mostly based on the spacing between the rebars. Okay, so there is another requirement for how much bulk volume of coarse aggregates you can use that we probably don't need it for now, but I'm gonna insert the table here anyways. This will be the bulk volume of dry rotted, so bulk volume of dry, and I hope you remember this one, the dry rotted bulk volume that we did in the lab, and we also covered in the class. So bulk volume of dry rotted coarse aggregates, and we based on an NMAS, or nominal maximum aggregate size. Nominal maximum aggregate size, right? So I'm going to insert that over here as well. All right. And then before we continue to the next step, there is two more things to consider: the adjustments. So coarse aggregates. So coarse aggregate adjustments. The first one is if we call coarse aggregates, if we need to increase, if we consider the slump, we're going to talk about the slump later on. So if we consider to reduce slump, increase coarse aggregates by 10%. And an example is for pavement productions. Example in pavement production. Right? And the other example, if you want to increase the slump, if you want to have a more workable concrete, so to increase the slump, decrease coarse aggregate by 10%. And another example for this one, when you want to have more slump or more fluidity or more workability of concrete, this is for concrete pumping. So when you pump the concrete into a higher, let's say you are building a high-rise building and you want to pump concrete into the higher floors, for the floor slabs, you need a more workable concrete, or more fluid concrete, or increases. You need to have a higher slump. That's when you decrease the amount of coarse aggregates, right? So that's pretty much what we need to know about the coarse aggregates. That was step 3, and then step 4 is, so step 4, that's how much air content you need. So percent air content requirements. Right? So again, ACI, we are following the ACI design method here. And ACI has another table for that based on nominal maximum aggregate size, you have different air content requirements. And you basically have two types of concrete. So based on, this is ACI table, ACI table. So based on nominal maximum aggregate size, nominal maximum aggregate size, that's, you have different aggregate size. Oops. You have two types of concrete for non-air entrained or for air entrained concrete. Then you will have different air content requirements that I'm going to post this table over here as well. So again, these are not the things that we need to remember. We just need to know how to use these tables to follow the mixed design process. And then the next step is, so step 5, we need to know how much or what kind of workability we need, or so workability requirements. As we mentioned, workability is basically measured with slump. So slump is showing ease of placing the concrete, consolidation, so consolidating and finishing. So when we are measuring a slump, we are basically measuring how easy it is to place the concrete, how easy it is for the concrete to consolidate, and how easy it is to finish the concrete for a smooth surface. And the desired condition is to have highest slump with no segregation. Or excessive bleeding. So when you have segregation or bleeding, segregation and bleeding means that the aggregates and the paste are falling apart. And when you pour the concrete into the slump cone, and when you release the cone, or when you remove the cone, you're going to see your aggregates are segregated from the paste, or you have a watery paste forming around the aggregates. I have examples of these that I'm going to post here in the notes, that you're going to see it, how it looks like. So These are examples of segregation and bleeding, and this is for a perfect slump. So we don't want to see these two to happen, and we definitely want to see a perfect slump. And if we have low slump, we can increase slump. So increase slump with admixtures. So there's certain chemical admixtures that you can add to the mix, and it increases the workability of the mix or a slump. Or you can basically add it rounded aggregates. But again, if you have too much rounded aggregates, you're going to have less strength. Although you have a workable concrete, but you have less strength. And you might ask, we never saw a slump, or we never did a slump test in the lab. So basically a slump is you have a steel plate, and then you have a cone, right, that you pour concrete inside in 3 levels. So let me, this is the first 1/3 of the height of the cone, and you place a rod. You rod it basically for 25 times per layer, and then you add another 1/3, and you rod again to make sure that the concrete is already consolidated, and then you add the last 1/3, and you do the rodding again. And once you finish the surface, right, you finish this, there is another, you basically use the rod. It's a metal rod. You use that one to finish the surface. And once you are done with the finishing, you basically removing the cone. You remove the cone, and what you do is you just put the cone upside down right next to the concrete, right? So you remove the cone, and you have your concrete sample here, and you just place the cone upside down right next to it, and then you put the rod on top of it, right? This is the metal rod. And after you remove the cone from the concrete starts to shrink, or we call it a slump. The concrete starts to slump. And when the concrete slumps, it goes lower, right? The level goes down, and then the difference between the slumped concrete and the actual height of the top of the cone, that's how much slump you have. This is measured in inches or millimeters, right? And based on, again, for the mix design, based on different applications, again, another ACI table here, that based on different construction applications, so based on concrete applications, you have a range of slump. So slump range in terms of maximum and minimum, right? So I'm gonna put that up here, and then the next step is water content, which we can go over next session. So